Making sense of continuous data is very similar to making sense of grouped discrete data. We still want to have a range or an interval for the different values because any one value is actually potentially impossible to attain. Let me give you an example. IMDb scores, and I'm limiting it to movies where there's at least 1,000 ratings. So at least 1,000 different people have given their rating for a movie. IMDb only tells you maybe 8.1 for a movie, but that's rounded. It only rounds it to one decimal place. It's possible that it's actually 8.1, 2, 3, 9, 4, 7. Any number could be possible, in this case, any rational number. But we need to not limit ourselves to just movies that get exactly 0, exactly 0.1, exactly 0.2, because very few movies are going to get exactly this much. They're mostly going to be decimals in between those numbers that it displays. I'm going to do a double inequality or a compound inequality like this. So this is saying that to be in this first row, your score x needs to be at least, right, greater than or equal to, so at least 0 and less than 0.5. Then the next one is at least 0.5 and less than 1. The thing to note here is that I'm getting rid of ambiguity. 0.5 shows up once in this row and once in this row, but notice in order to be in the first row, you're actually less than 0.5. If you were exactly 0.5, you'd be in the second row. So I can do the same thing for the rest of these. And actually, let me change the ones that I'm going to look at, because if we look at the histogram over here, or the chart over here, we're going to notice that they don't start getting tall until around this area. So let me skip a few of the smaller ones and instead put in 7 is less than or equal to x is less than 7.5. 7.5 is less than or equal to x is less than 8. And then the highest possible score would be 10. That is never actually achieved because everyone would have to give you exactly a 10 to get there, and that just has never happened. So I have a lot of movies in this database. It's over 50,000 movies that have at least 1,000 ratings. And so when I fill in these frequencies here, I'm doing this from notes. I'm not counting up these tiny little lines here. So 0 of them are less than 1. 26, 84, 163 are between 2 and 2.5, 236, going down between 7 and 7.5. That's actually the highest and most common interval. That's 8,812. 7,500 are between 7.5 and 8. And then between 9.5 and 10, there's 433. And looking at these numbers, right, there's a wide range in how big these numbers are. Obviously, they start at 0. There's a few that are in 2 digits, 3 digits. These are much bigger than the rest. And so if I plot it as it is in this form, this is a histogram, which is very similar to a column chart, very similar to a bar chart. There's a few differences. The columns are touching, whereas with discrete data, you usually don't have them touching. Although in the group discrete data, I did have them touching. And also, it's continuous data. So looking at this histogram, I can tell the mode right away. The mode is the column that represents between 7 and 7.5, which if we look at the frequency table, at least for the ones that are down, that is easily the highest one. And also, I can see that it is negatively skewed, right? There's a tail on the left side. More of the data points are to the left or to the negative direction of the mode. And this gives me a great sense of what's going on. The only thing that I could potentially do better is I don't really have a good sense of how big 8,812 is in this context. And I know that it's between 8,000 and 9,000, as you can see up here, but how common is that really? In order to do that, we'd have to know how many movies there are and make a relative frequency plot instead, a relative frequency histogram. And there's actually 54,682 ratings, but for simplicity, let's just say that there are 50,000 movies where at least 1,000 people have rated them. So in order to make the relative frequency, I'm going to take the frequency and divide by the number of movies we're looking at, which is 50,000. Of course, 0 divided by 50,000 is still 0. 26 over 50,000 is 0.00052. If a movie is that bad, that's pretty rare. Okay, so we have all the relative frequencies here. As you might expect, the highest relative frequency is the same as the highest frequency because I just divided all the frequencies by the same number. It's not going to change how big they are relative to each other. It just makes it so that they all add up to 1. Instead of adding up to 50,000 by just counting the number of movies, I'm dividing by the number of movies so they add up to 1, which is 50,000 divided by 50,000. So what we're going to do here, in order to make this a relative frequency histogram, I just need to change my y-axis. Right? My x-axis is still going to be score, or average rating. My y-axis before was frequency, and we saw that it maxed out at 8,812, but I'm going to change this to relative frequency. All I have to do this is change the scale. 9,000 in frequency converted to relative frequency. Well, 9,000 divided by 50,000 is 0.18, and I can change the rest of the y-axis in the same way. And now I see that this may be more useful because I can tell, around 18% of movies are rated between 7 and 7.5. Around 16% are rated between 6.5 and 7. Same thing over here. And if I wanted to see what a typical movie was, well, if I add up these 4 sections, maybe that's about half of all movies are in that range. So making it into a relative frequency histogram gives me a better sense of, well, gosh, only 2% of movies are between 4 and 4.5 on IMDb, and all the ones lower than that are even smaller. So to be between 4 and 4.5 is pretty rare. Similarly, to be above 9.5 is extremely rare. Most things are in the middle in this negatively skewed distribution where the mode is the interval between 7 and 7.5.